The purpose of this video will be to give a brief overview of Galois descent. So the basic question of descent is as follows. How do you go backwards from base change or scalar extension? So there's a fundamental problem with this, which is that information is typically lost when one extends scalars. So that is to say, suppose you have two algebras defined over some field. It may well be the case that although these two algebras are not isomorphic, that they may become isomorphic after extending scalars in a suitable way. So one typically says in this context that these two algebras would be twisted forms of one another. The method that descent gives us is a way to introduce additional information, which is generically referred to as descent data, that tells us how to go backwards. To gain some intuition about how descent data is going to work, let's consider the more geometric situation where we have an open covering of a topological space. So in this context, if we have some space X covered by these three open sets U, V, and W, then given some sort of an object or family of objects on X, we might imagine like families of vector spaces or things like that, like vector bundle, then we can take such an object on X and restrict it to these three particular open sets. This is the analog of a base or a scalar extension. We take something on X and we get something on the disjoint union of the three open sets. Now conversely though, given something on this disjoint union of three open sets, we'd like to say what we need to do to go back and get something on X. Well, this is a familiar concept. To go backwards, what we really need is often referred to as gluing data. What we need is ways of taking whatever our family is on U, so given some family on U, some family on V, and some family on W, take our family on U, restrict it to, for example, U intersect V, and we need to identify it in some way, via some, let's say, phi U V, with the family on V restricted to U intersect V. And these identifications need to be compatible with respect to triple overlaps. That is, if I look at my identification of U with W and W with V, then that gives me one identification of U and V on the place where these all three open sets overlap, and that should be the same identification that I pick with U and V originally. So there's this well-known compatibility, phi of UV, phi of VW, should be equal to phi of UW, at least on this triple overlap where these things make sense. So in the context of families of objects on a topological space, descent data exactly consists of choices of these isomorphisms, phi UV, such that for every triple overlap we have this, this condition holding. Transitioning to something a little bit closer to a Galois extension, but still drawing our intuition from topology, one could consider the example of a covering space. So just the same question could be asked, given a family of objects on X, one could then pull it back to a family of objects on the covering space. And then the question is, given a family of objects on the covering space, what do I need to know in order to get a family back down on X? How do I know that it came from X, and what additional information do I need to determine the family on X? Well, what you can see is that if my family on the covering space, and we'll assume that it's a regular so-called Galois covering space with group of deck transformations G, what we need to know is that certainly if I have, if all these things came from pulling something back over here, then that means my object, restricted to each point, has to be the same along each fiber, right? So the points that map to this point downstairs are these 4 points as I've drawn them. I'm pretending these little green lines represent what my particular family looks like over that point, and all these green lines had better be isomorphic. Well, one way to kind of encapsulate that in a more family-oriented way is that the deck transformation groups are going to move these various green lines to each other and permute them around. And these isomorphisms, and what I need is that if I permute these things by deck transformations, then my family on x tilde should look the same. More strongly, what we really want for descent data is we would like the group of deck transformations, which a priori just acts on x tilde, to in fact act on the entire family. So that is to say, what we want is we want for each g and g, we want some phi g, which gives an isomorphism between the family on x tilde and the family after pulling back by using the deck transformation. So you can call it like the pullback g of the family in x tilde. And what we would like is that this gives a way of extending the Galois action, or the deck transformations, to acting on this, to acting on the family. So deck transformations and covering spaces are, of course, very close to Galois theory of fields, and this intuition we will be able to directly translate to give us the right definition for descent for fields. All right, now let's finally do Galois descent for the field case. So the problem, let me restate, is as follows. Let's imagine we have some field extension, which is Galois with group G, finite extension. Then this gives us a way of starting with, for example, algebras defined over F, extending them up to E by tensor product, scalar extension. And the question is, if I conversely have some algebra over E, what additional information do I need in order to figure out an algebra where it might have come from? So how can I start from an object like this and recover the A? Well, of course, in the case where we know that it came from A, you can actually see how this must work. Because what we can do is we can look at the action of the Galois group on A tensor E via the action on the second factor. And you can simply take invariance under the Galois group. So the things which are G invariant here, it follows very easily from the basic Galois theory that this is actually naturally isomorphic to simply A. And so what this lets us say is that so long as we have an action of the Galois group upstairs, a nice action, like we have over here, that gives us a way of maybe going back downstairs, which aligns with our intuition from the covering space theory, where descent data was given by extending the action from the covering space to the family on the covering space. A plays the role of the family, E plays the role of the covering space. So we would like to extend the action from E to the family over the covering space, in this case A tensor E. Well, this gives us an idea of what we should put in here for the question mark. Given an arbitrary algebra over E, what do I need to know in order to say, to give an algebra where it came from? What I need is an action of the Galois group. So such an action that generalizes this one is called a semilinear action, and it goes like this. So we want an action of G on B. Now remember that B is a vector space over E, not just over F. It's an algebra over E and a vector space over E, such that sigma on lambda B for lambda in E and B in B, instead of the scalar lambda pulling out like an E linear map, we want this actually to be compatible with the Galois action. Just in analogy with the covering space theory, we're extending the action on the covering space to this family, the covering space itself being thought of as analogous to E. We want the action on E to really stay in this picture in a compatible way. So such an action is called a semilinear action. And given such a semilinear action, so if we want to call this, let's say, dot, will be, So dot there will be a semilinear action. Then again, we can take invariance and get something downstairs on F. And the theorem of descent goes as follows. It says that the category of, let's say, vector spaces or algebras or similar such things, let me just say algebras over F, the category of algebras over F, is equivalent to the category of algebras over E equipped with a semilinear action. Of the Galois group. And so descent says that this is an equivalence of categories where we have, on the one hand, taking an algebra to A to insert E with the standard action on the second component, and on the other side, B goes to the G invariance of B. All right then, so let's then talk about why this theorem actually holds, why I get this equivalence of categories. Part of this we've already just seen. What I really have to check is that these two functors give me mutually inverse, or kind of mutually inverse, at least up to natural isomorphisms. And what we've already seen is that if we have an F algebra and we extend scalars to L, and then go ahead and take invariance, what I get is naturally just A back again, canonically identified with A. So that gives me half of what I need. The other half is slightly more interesting. And let's start by forgetting about the algebra structure and just thinking about these as vector spaces. Okay? So let's state, pretend we're stating the exact same theorem, but not for algebras, but for vector spaces. So how does the explanation go then? Well, we start with some vector space B, together with a semilinear action. We extend scalars, we take G invariance, and then we extend scalars back up to L. And the question is, why are things on either side actually naturally equivalent? Or naturally isomorphic, excuse me. Well, let's really think about what is the semilinear action like on B. As is probably familiar to many people, if I just have an action of a group on some vector space, then this defines a module structure for that vector space under the group algebra. Something similar but slightly different happens in the case of a semilinear action. So what we can do is, just like in the case of the group algebra, define some indeterminant, which I'll call a U sub sigma, for every element sigma in the group. And having done this, we can define a module structure, some sort of an action, if you will, where U sub sigma acts on the B's by doing sigma of B. Then it's easy to see that if you just define it this way, that the U sigma U tau defined to be U sigma tau gives a perfectly reasonable definition for an action. The trick, though, is that what I also have here is I have scalar multiplication by L. And so if you consider how scalar multiplication by L works, then we see that if I do scalar multiplication by some x in L times some vector B, and then I act by sigma, what I don't get is that U sigma acts by a linear map and that the U commutes past the U sigma, right? Because what this action looks like, so I want to say U sigma acting on x acting on B, what that looks like, so this is going to be U sigma x acting on B is going to act by a scalar multiplication, and the action here is via sigma, and the semilinearity exactly tells me that I get this, which if I unpack it is the same as U of x, U sigma acting on B. Scalar multiplying by sigma of x, then the U sigma after the U sigma action on B. Well, what this means is that the x, unlike in the group algebra, is not a central element in the algebra, but commutes past the U sigma by doing the Galois automorphism. And the algebra that I get by defining this multiplication law So as a vector space looks like an L vector space, if you will, on the left with these U sigmas, but with this multiplication law is usually written LG1. It's called a so-called trivial cross product algebra. So in fact, this algebra that I get turns out to be isomorphic to the endomorphisms of L as an F vector space. Well, one way to see this is, it's easy to check just by kind of counting here that these are matrices of a certain size, degree of L by degree of L. And this algebra, I can kind of see how big it is. These two things have actually the same dimension. Right here we have degree of L times order of G. Order of G is the degree of L, again, by the basic idea of Galois theory. These two things have the same dimension, and I have a map from this thing into this endomorphism algebra, which I've just defined, because L in particular is a G module with a semilinear action. It's a kind of L has a semilinear action by G, and so that gives me a map from here into the endomorphisms. But then, so therefore, L itself is a module for this, but these things have the same dimension. And what you can check after a little bit of work is that this map is actually injective. So the injectivity of this map is exactly, if you translate it, a standard result called Dedekin's lemma. Dedekin's lemma, which is a standard result you can find in most treatments of Galois theory. So it translates to just saying that this is injective. They have the same dimension, they're vector spaces, it's an isomorphism. All right, so, so what that tells me is that this algebra that I have is isomorphic to endomorphisms of a vector space, and therefore this is a simple finite dimensional algebra. The structure theory of such things tells me that this thing has a unique simple module. That is to say, any finite dimensional module over this algebra is a sum, is semi-simple, a sum of simples, and there's only one simple module around. It turns out to be L, just by a quick check, because L is a simple module you can easily see. And so what that tells us is that an arbitrary B, to make a long story short, what we have is that an arbitrary B is isomorphic in terms of an module over this, which is to say it's isomorphic as a vector space with semilinear action to just a bunch of copies of L. That's what this whole thing bought me. Well, as a semilinear thing, it's like that. But then if I act by G and take invariance, that gives me a bunch of copies of F. And then if I scalar extend again, this gives me a bunch of copies of L. And what I find is that there's a canonical way of identifying what's in the beginning and in the end. In fact, if you think about it, there's a natural map from the invariance to there, which upon scalar extension gives you a natural map from this to there. And the fact that we can trace through the explicit module structure and what's happening tells us that this is actually an isomorphism. And so we get that on the level of vector spaces, this gives me a mutually inverse set of functors up to natural isomorphism. What remains to do is to lift this to algebras. And the way to see what's happening there is to make an observation, which I'm not going to prove in detail, but which you can just simply check. And that is the observation is that if you look at the map of vector spaces, of categories of vector spaces, so L spaces with semilinear action, and F spaces, it's just F spaces, that if you take invariance on the one hand, and on the other hand you extend scalars, then what you find is that these play nice with respect to tensor product structure. That is to say, over here, if you take two vector spaces with semilinear action and you tensor them together, you get a new vector space with semilinear action, where kind of sigma acts via sigma tensor sigma, acts by sigma in both factor. And if you have two F spaces, you can tensor them and get an F space. So you have kind of tensor product structures on both sides. And these mutually isomorphic, mutually inverse up to natural isomorphism functors give you actually respect to this tensor product structure. And so what does that say? That says that if you have an algebra with semilinear action, in other words, if the semilinear action is acting as algebra, is respecting the algebra structure, then you can phrase that in terms of vector spaces with and tensor products of vector spaces and etc. Right? Because that's what an algebra is. It's, A tensor A goes to A and a bunch of compatibilities, etc. And if you have so if you have this structure and compatible action, then on the other side you just get an F algebra over there by taking invariance. And so the point is that because this equivalence of categories of vector spaces preserves the tensor, you can enhance or decorate this equivalence with structures involving vector spaces and in the language of tensors. And so in particular, you get an equivalence of categories of algebras, etc. All right, so that's a brief summary of why descent is true in the Galois case.